Hello and welcome back to the Museum of Everything Else. Last week we had a look at Everyday Electronics, June 1976. We had a look at the wah-wah pedal, the enlarger meter, the continuity tester and the peak level indicator. Well, last week we had a sneak peek at what was to come in the July 1976. That is the auto-cool, the Accented Metronome, the RFAF signal generator and the mysterious Aqua guard, which may just be a moisture detecting thing. But I promised I was going to find it, so there it is. We found it. Here it is. This is July 1976. So yeah, let's without further ado, let's have a look through this one. So I'm just going to let you know that next week potentially we're going to break from the norm. It may not be the next one. I'm not very good with my months, so I need to run through them all and remember which one's after July. August. So yeah, we may not be looking at August next time, but we may. Let me know what you think. If you want to look at August, or you think there's a little bit of a... I found another interesting magazine, so maybe we'll look at that. Anyway, let's have a little peek at what we've got in July 1976, shall we? So starting off, oh my gosh, it's him again. This was in the one before. This was in May, which I shot last week. And yeah, style a component, purchase a home radio catalogue. And like I said, one day we will send one of these off just out of interest. Oh, that looks really cool. That looks like a pretty interesting radio kit. Like, looks like a pretty cool little fun kit for £6.30 including VAT. Anyway, so yeah, as usual, these things are littered with you know, things that you can purchase, like obviously your extractor fan, windscreen wiper control, because that sometimes doesn't come as standard on some on your vehicles in July 1976, of course. Back again with the Electro Time. This is a running theme. They're still trying to shift these like crazy. This one's got a nicer case, I think. I haven't seen this one in the adverts before, but that's a nice square version of this dodgy circular one. And it's cheaper. Oof, very nice. And we got a pretty nice Marshalls that used to be in London. No, it doesn't say brackets London Limited, but there's a number of different places. We've got it up on Cricklewood Broadway, Northwest London, West Regent Street in Glasgow, Straits Parades Fish Pond. So yeah, maybe let me know if this is still about Marshalls. And there was even one in Paris. Wow. Anyway, this is the mysterious thing that we were trying to figure out. Well, I was trying to figure out yesterday, and now I've quickly looked at it. It looks exactly like what I thought it is. So if you've gone to school recently and you've gone to your electronics class, you've probably built this. In fact, my mum taught design technology at school, and at the end of the year, sometimes there's a bunch of electronic projects which the kids haven't actually picked up, and there's loads of we got boxes. Not boxes, that's an overstate. We've got a box full of like projects like this one, the probe one. Basically, this is a sort of thing. It can be used for a number of different things. What happens is the water connects between these two probes inside the circuit and makes the connection and shorts the connection and makes the circuit, you know, go bzzz. And this is like, in fact, I see it in a lot of places. I'm not sure how they're going to be selling it on this one, but there's one for blind people trying to fill up a cup of tea. There's people trying to figure out a very rudimentary, see if your plant needs watering kind of thing. But in this one, there's a picture of, yeah, the Aqua Guard. Described here is a multi-purpose device for which many applications will be found in the home, school laboratory, and on marine craft. It provides a loud, audible warning signal whenever a special probe is immersed in or bridged by water. Yeah, it's pretty cool. I mean, you could just make it work like that. Okay, so let's have a chat. Let's read through it. Moisture detectors make use of the fact that ordinary tap water possesses a comparatively low electrical resistivity. This is due to the presence of dissolved impurities such as mineral salts, which ease the passage of current through what would otherwise be a very high resistance. The circuit of a fairly typical detector is shown in Figure 1. The probe consists merely of conducting metal rods which are spaced by a small distance. The resistance between these probes in free air is also almost infinite. In this situation, the base of TR1, right there, is open circuit, and assuming this transistor is of the silicon variety, only a very small leakage current will flow through the device, and this will prove insufficient to provide base bias for transistor 2 right there, which in consequence remains turned off. But if the probes are immersed in water, a resistance in the water of tens of kiloohms appears between base of TR1 and the positive supply line. Ooh. As TR1 is an NPN transistor, it becomes forward biased and current flows readily between its collector-emitter junction. This will have the effect of placing a low resistance between the positive supply and TR2's base, with the result that this transistor also turns on, and due to its own current gain passes a high collector current. The relay coil, I'm slowly going into the posh voice, it's like, the relay coil energizes and generates a magnetic field, which closes the contacts on the relay and rings the bell. Ding-a-ling-ding-ding, I see. Although the circuit of figure 1 is both simple and reliable, it has the disadvantage of requiring a relay and also a sounding device. A far better design would employ an electronic sound generator driving a small loudspeaker, and electromagnetic relay should be eliminated. To this end, the circuit of figure 2 was developed. The heart of this device is a multi-vibrator oscillator comprising of TR1 and TR2. Yes, TR1 and TR2, sorry, over there. So it's just basically the same as that, but with two transistors acting like a multi-vibrator oscillator with a little speaker, a tiny little speaker on this little BFY52. Ooh. Funky. Those who have studied previous circuits which make use of multivibrator as an audio oscillator may be surprised to find capacitors with values as low as 0.01 microfarads being used in a circuit designed to produce an output of approximately 1 kilohertz. The method in this particular brand of madness is to give R3 and R4 comparatively high values, so that any changes in resistance between the probes, due to variation in the water's resistivity, corrosion of the probes, etc., has a minimal effect on the oscillator's frequency. Or to put it another way, the ratio between the resistance of the water and the values R3 and R4 are fairly high. I see. So they're keeping the capacitors pretty low, so they can keep these resistors pretty high to reduce the effect that the probe actually has on the circuit and the resistance that adds. So it's pretty funky. However, I've got to be honest, I love the relay one. It's beautiful. Imagine a doorbell, but instead of a button, you had to lick your finger and touch it, or something like that. It wouldn't be the most hygienic one in such a time like this. Picture of the case, it's got space for the battery, and then there's look at that, the strip board's stuck sideways, mounted to the side of the panel of the enclosure. That's pretty cool. Let's have a look at the strip board layout, which I guess is this one. Yes, we're starting to get a hang of these magazines. So this is the strip board layout. Yet again, there's a couple of, these are the big boy capacitors, and there's, oh yeah, what a beauty. So, look at that. And there's even a circuit for using 2 probes. What for? I'm not really sure. I guess, I don't know. What name an application where you would require 2 probes to turn on? Can't think of one off the top of my head. Oh, here we go. This is a little bit more interesting, the metronome. This is the reason why I got this one along again, because obviously we've got the metronome, and in previous magazines, like I've mentioned, like the Lightning Chess in May 76, where it was just a timer, but this actually looks a little bit tech, but I guess that's because it is also adding a accent on, it could be any of the actual any of the triggers. I'll just read you through it, because it did say what it was in the last episode of this, but let's have a look through. Basically, the Accented Metronome consists of 2 pulse generators, one being triggered by the other, as shown in the block diagram to the left. So we've got a pulse generator here, the main one, and it's, okay. The fast generator is a free-running unijunction relaxation oscillator, and the output is fed directly to the amplifier and heard in a loudspeaker. The frequency of this generator is controlled by a potentiometer fixed to the front panel. Ooh. An output from the first generator is fed to the second generator, where it causes the timing capacitor here to charge up. It may take several input pulses to produce an output pulse. The number of input pulses required to produce an output coincident with every second, third, or fourth first generator pulse can be set by the presets in the circuit, thereby accenting the second, third, or fourth beat. That's interesting. I wonder how they do that. That's pretty strange. Oh, wow. So they're charging up a capacitor and you've got to trim it. Wow, that is a weird design. That's pretty funky. Interesting part is the frequency divider in this because, yeah, it's from what it's saying here, it's charging up the capacitor in different levels because a single pulse doesn't charge it up much, I guess. The static voltage across R2 is insufficient to turn on TR2. Where are we? R2, TR2, interesting. But the pulses produced across R2 will momentarily turn on TR2. Okay. This is of course provided that S1 is in position 2, okay, 3 or 4. Oh yeah, there's no, it doesn't get anything from mode 1. Okay, so I guess if mode 1 isn't there, it's just ticking. Interesting. These resistors control the level of current that is pulsed through TR2. The transistor TR2 collector feeds a second unijunction relaxation oscillator. Preset VR2 is adjusted so that after one pulse of current, the voltage across C2 is just below the triggering point of TR3. The next pulse therefore causes TR3 to trigger, and a pulse is simultaneously produced across R3 and R5. Oh, yeah. After a further 2 pulses, TR3 will again be triggered, and so TR2 and TR3 operate as a divide by 2 circuit. Ooh. Components VR3 and VR4 are adjusted for slightly lower currents through TR2, so that 3 and 4 pulses respectively are required before TR3 triggers. Thus, divisions of 3 and 4 are provided. That's a really quite a strange setup. So it seems a little bit finicky to me, and potentially that's mad. So in order to get accents to make a dividing circuit, you're actually choosing how much current's going into the emitter of this transistor to charge this capacitor up. And the more that goes in, the less it's divided. But I guess if you are making this a bit variable, then you can make quite a weird random thing. That's really strange. What other circuits do you know that use this sort of thing? That might be very obvious, I don't know. That uses adjustable amounts of currents to change the subdivision of a dividing down oscillator. That's really funky. Could be cool, like if you had a CV input for that, maybe it would adjust it and be like a weird divide down thingamajiggy. Here's an image of the strip board layout. Like I said before, this is shot in 4K, so if you want to screenshot these things, also there is a link below so you can find these magazines, because amazingly there are actually a number of links where all of the Electronics Today magazines and many others have actually all just been scanned, but you haven't got an annoying person like me just going through it reasonably slowly. So here's an image of it as well. Look at that with the trim pots. You could also add these trim pots to the front. At the same time, you could remove the mode switch and just have one trim pot and use that as like a weird, yeah, you could make like a weird divide down oscillator synth thing if you sped up the first transistor, the metronome, to be audio rate. That could be quite funky. Huh. Oh, next month looks good. Look at those boxes. I swear, like half of these projects, the nicest thing about them are the boxes. For Your Entertainment by Adrian Hope. More on resistance and proof that if you are dealing with electricity, it helps to know Ohm's law. Like almost everyone else, I suspect I was horrified by my last winter's electricity bill. I paid it, but asked for the meter to be checked. I was equally horrified by what happened next. The LEB official who arrived to reassure me that my meter was in fact correct offered to run an on-the-spot check to prove it was reading correctly. We'll take that 1 kilowatt fire, he said, pointing at an electric fire that I had for 10 years, and check the meter with it, because the meter wheel revolves 225 times for 1 kilowatt hour. Wow, that's a lot of movement. I forget about these very old school style meters. That's mad. We only need to switch on the fire, time 4 minutes with a watch, and check the wheel turns 15 times. I tried unsuccessfully to point out to the official the fallacies in this approach. An approach, incidentally, that is widely recommended as a convenient DIY meter check. Ooh. I can see that at least 3 fallacies, but readers may well be able to think of some more. First, it is quite impossible to say whether any wheel has made exactly 15 revolutions in exactly 4 minutes. But even the slightest error at this level will be puffed up into a massive error when converted to a period of 3 months. Conversely, even a medium-sized error that appears over 2 or 3 months will not show up in 4 minutes. Even more important, it is quite absurd to assume that every electric fire, which is normally rated at 1 kilowatt, does in fact have the exact resistance needed to produce 1000 watts on a 240 volt supply. He's even said 57.6 ohms. As home constructors well know, all electrical components have a tolerance, and even a brand new element could well be 10% out, or change 10% in value over the years of use. This would produce a similar change in the wattage rating of the fire, which is hardly insignificant. Even if it doesn't show on the clumsy revolution test that the official had in mind, perhaps most relevant, the electric board is legally entitled to let the supply voltage vary by 6%. And a 6% drop on 240 volts produces an 11% change in wattage. All manner of combinations are possible, one error compensating for another and so on, making a mockery of the test run. For instance, a meter error of 11%, meaning 11 extra pounds on a £100 quarterly bill, would vanish if the voltage happened to be 6% out at that time check. The LEB press office subsequently gave a reassurance that the official who visited me was well out of line and should never have suggested such an absurd check. Ooh. The standard procedure for checking a meter is to strap a rotating standard meter alongside the consumer meter and compare results. If a consumer is still unhappy, he can even demand an independent check. But do please think twice before putting your electricity board to the expense of running such a check. Most electricity bills are now higher than ever simply because the price of electricity has gone up, not because the meter has clocked up more units. Every full test that is run costs the electricity board money, which in the end puts more money on the price of electricity. Touching more on your career in electronics, this is, wow, what is that? That looks mad. That's machine. Oh yeah, of course you know what that is. That massive thing is the L9000 mini computer. Of course. Oh, here we go, Jack Plug and Family, a family favourite. Our car's gone. Look, there's a note. It says, I've pinched your car. You made the mistake of leaving your magazine on the seat. It was open at the car safe system page, so I soon found out the switch that turned your alarm off. Yours, a well-wisher. P.S. Isn't EveryDay Electronics a wonderful magazine? I'm ordering a copy right away. These people know what it's about. Look at that massive bulb screen at the back. Oh, checking out a computer-controlled HAZM system for motorways at Ferranti in Manchester before delivery to Australia. The computer does the toll booth accounting and provides statistical data as well as controlling the hazard signs, which can be seen in the background. Oh, yeah. Oh, that's just in the context. That just looks like an awesome, like old school laboratory screen, but it's just a screen for a road. Fog 35, stay slow. But wow, they're shipping that off to Australia. Wow, it's going to be quite a big chunk of postage. Oh, look at that fisheye picture. That is mean. A digital watch employing ICS manufactured by RCA. And then moving on, we've got an RF-AF signal generator. This is another pretty funky. It's just a relaxation oscillator. Again, they just love doing circuits with these, just in different packages. This radio frequency audio frequency signal generator is an instrument which can provide a tone modulated radio frequency signal or a single audio frequency tone. The RF signal is used for quick checks in locating the source of a fault in intermediate frequency and radio frequency stages. And as an aid in alignment or trimming, the audio frequency signal allows rapid stage-by-stage checks of audio frequency amplifiers or the AF section of a receiver. With home-built equipment, there can be some difficulty in calibrating the RF bands over which a generator can be tuned. In the generator described here, this is overcome by using air cord fixed inductance coils, which are manufactured to a high degree of accuracy. In conjunction with a particular variable capacitor, it is then possible to fit a ready calibrated scale to read off frequencies. More details about the use of an RF-AF signal generator are given later, and it can be seen to be a very useful piece of test equipment. This is actually quite a simple design for just a woo. So if you want to get your Heim back on, make your own DIY audio frequency signal generator, then maybe this is it. It's like these are the coils that they're talking about too. So you don't need to actually calibrate it. You use these high-tech inductance coils. It's pretty funky. This one goes proper music from outer space on the drawing. Lots of panel wiring here for this one. That looks amazing. These coils look really cool as well. Oh, just look at that beauty. Look at that picture. There it is there, and then here's the plan. Obviously, like I said, remember, and you can even print this out. Oh, this is 2/3 full size. So I don't know. I'm wondering how you would actually do that. How do you get that? Especially in 1976, would you just draw this on? Or how would you blow that up? Would you use an enlarger? I'm not sure how you would do that at home. Take this. This is a 2/3 scale image. Would you just draw it? And here's the simple strip board layout for that as well. It's looking very nice and simple, yeah, with the different coils. That's really cool. Just look at it. Oh yes, we come to our favourite 1976 Rick and Morty. This is the one. The Extraordinary Experiments of Professor Ernest Evershaw. Yes, I like this bit. This is probably my favourite part of Everyday Electronics, I gotta be honest. He's I still need to understand which one's Ernest and which one's Bob. Is it? Yeah, Bob. I guess this is Bob. Hello, I'm Bob. That's Is that a mustache or is that his mouth open? I'm not quite sure. And then, yeah, Ernest Evershaw. Oh, yes. Pressing a few buttons on the panel, the prof removed the 6 stationary dots so as to leave only the single movable spot on the screen. Oh! Looking back, Bob is in a control seat of a pilot simulator that Professor Ernest Evershaw has built, and it's a little bit more complicated of a simulation than Bob initially thought. Anyway, let's carry on. Pressing a few buttons on the panel, the prof removed the 6 stationary dots so as to leave only the single movable spot on the screen. The glowing trails of Bob's figures and squiggles had by now nearly faded from the screen. Now it was the prof's turn to work the pedals and joystick, and Bob watched in amazement as prof used the moving spots with its glowing yellow tail to trace out a simple circuit diagram on the view screen. Look! No hands and no feet, the prof remarked, as Bob was astonished to see that although the prof had lifted his hands and feet clear of the controls were still moving, and the spot was tracing its way over the circuit diagram again and again, so that therefore the yellow line could fade out, the spot had traced over them again. This was everything the prof had drawn on the view screen, being preserved in the view. Oh wow, that's cool. So Professor has drawn something onto the actual cathode ray oscilloscope style screen, and now the computer's just constantly drawing over and over again so it doesn't fade away. Wow, technology. Soon Bob saw the explanation for this strange occurrence. Seated in another robot tester nearby was the prof's latest experimental robot. In front of it was another view screen, to which the prof had relayed a copy of his circuit diagram. The robot was working with the pedals and joystick, tracing the diagram over and over. Here you could see, Bob, how the circuit very much resembles the circuit for vertical and horizontal shift controls, but the extra capacitor is able to give you a delayed action effect. There are quite a number of variations which can be made around this basic circuit. This could make a good exhibition project for our school's science fair, exclaimed Bob. I'm sure we could rig up a set of pedals and a joystick controlling potentiometers connected through a circuit such as this to a DC oscilloscope. Then visitors could have a go on these controls. It's quite fun, very interesting, and I'm sure they would be impressed. Actually, that's pretty cool for the museum. I might make something like this. Obviously, it's not. I don't have the plans for Professor Ernest Evershaw's duplication robot, but the joystick circuit. I mean, that's just pretty cool. Just plugging a joystick into an oscilloscope. But at the same time, then you may as well have Pong on it. Like an analog Pong. Oh, analog Pong. That might be the next one. Variation. The Prof agreed. One of the variations which could be used is this. He informed Bob, taking over the controls once more. The Prof overrode the robot, and by working the pedals and joystick deftly, altered the diagram to give the circuit a figure 2. The robot continued to trace this new circuit. This one is a bit more complicated, but it would make the equipment more interesting to use. You could build, say, this circuit on the vertical and the other one on the horizontal deflection potentiometers. Let's have a quick look at figure 2 before we forget. Ooh, a tricky effect, eh? What's going on here then, Prof? Now the Prof stopped the robot from his duty of tracing and retracing the circuit diagram, and as the robot went back to this other duty with the mysterious biscuit tins and the voltage breakdown tester, the Prof allowed the diagram to fade and brought the spot to the center of the screen. Now he asked Bob to take over the controls and keep the spot in the center of the screen. The Prof pressed some buttons and a number of circles appeared on the view screen like a bullseye target with the movable spot on the center. Now is the time to show you how the low frequency random noise can be used to test coordination of movement, the Prof told Bob, pressing another button to feed a random deflection signal to the spot on the view screen. The spot began to move away from the center of the screen, first one way, then the other, up, down, and from side to side. Bob found it was almost impossible for him to keep it inside the inner circle, and despite his most ardent efforts, it quite often went outside the second one too. Ooh. To add to the distraction, another visitor entered the laboratory. The new visitor was a young lady of about Bob's age. She was Susie, the sister of Bob's friend Paul. And in one hand she held an electrolytic capacitor. I think this is faulty, Prof. Susie began appealingly. I wonder whether you can find out for me. Meanwhile, Bob had switched off the robot tester, and as he came over to join Susie and the Prof, he heard the Prof saying, yes, certainly, Susie. The robot is testing and reforming a batch of electrolytic capacitors for me at the moment, and I can put this one of yours in with the others. What is Susie doing with this electrolytic capacitor, you ask? Well, we'll find out, I'm sure, very soon. The three of them went over to where the robot was working, and the Prof handed the electrolytic capacitor, which Susie had brought over to the robot. As the Prof gave the instructions to the robot, it opened one of the biscuit tins. Inside, Bob could see another electrolytic capacitor was clamped to an insulating panel. The robot quickly disconnected and removed this capacitor, which had by now been tested thoroughly, and clamped Susie's capacitor in the box. He connected two wires, one red and one black, to the capacitor and firmly closed the box. Now he connected the wires which came through the grommets in the side of the box to the voltage breakdown tester and began to increase the voltage. Bob saw that as with other capacitors, the voltage rose jerkily rather than steadily rising voltage. There was a random low frequency signal which caused the voltmeter and milliammeter to flicker unsteadily over the dials. The reason for this unsteady voltage rise, the Prof informed Bob, is that the capacitor is not merely being charged, it is also having its dielectric reformed. If an electrolytic capacitor becomes damaged, which can be easily done if a reverse charge or an AC voltage is fed into it, causing it to become reverse polarized, the layer of the aluminium oxide dielectric on the anode becomes uneven in the thickness, and its insulating properties are insufficient to withstand the full working voltages of the capacitor. The capacitor cannot be used at its full voltage until the damage has been repaired, and the robot is using the breakdown voltage tester to test and reform some of the electric capacitors right now. Ooh, very lovely. So we'll have a look at the back, the classifieds in the back. I guess this is called as classifieds. Oh yes, you can build your own treasure tracer kit. Only for £12.50 for a metal detector DIY. As seen on BBC One and BBC Two TV. Well, have you ever seen the Treasure Tracer Mark III on BBC One or BBC Two? Let me know. I wonder in what context that was. The case of a professional finish. Oh, look at that. Just look at those cases. They are beautiful. Ooh, this is the back page already. Oh, this is good. This fellow's funky. Imagine the thrill you'll feel. Imagine how impressed people will be when they're hearing a program on a modern radio you made yourself. That's how I feel when I play my synth. Oh well, that is the end of this one. Oh my gosh. Oh, the most ultimate. A fair few years ago, I had a chance to buy one of these for reasonably cheap, and I passed it up, and I don't know why, because damn, I wake up every night just in cold sweats thinking about that time, because like imagine being in a world where you could have purchased from Maplin's all the PCBs, metalwork, and drilled in everything, and the construction details for £1.50. If anybody knows the whereabouts of any of this sort of stuff, oh God, I wonder if it's linked. Maybe I should just try and build one out of stuff that's sitting about, because they look amazing. The panel and they have if you haven't seen the Maplin 4600 or its little brother, I can't remember what it's 3200 or 3800. It's got a little patching matrix over here. This one's got 4 oscillators. I can't remember exactly. It's like 3 filters and a bunch of ADSRs. It's absolutely awesome. Build your own electric organ. That's cool. This is all make it with Maplin. It's mad to think that Maplin, it changed so much, I can imagine. Like when I knew Maplin, it was just, you know, the high street shop that it was until it shut, much like Radio Shack. But I guess, yeah, this kind of stuff, it didn't really have this sort of stuff anymore. Oh, it's so sad. Oh, look at these decks. Look at those decks as well. Like they're all built into the same thing. Oh, that's beautiful. Anyway, that is the end of Everyday Electronics, July 1976. And like I said, next week I might be changing it up with a different one, because I found a couple that are a bit more synth orientated, and I sort of want to cover those. And then maybe at some point I'll come back to the August, because I think I have got the August one. I'll just have to look for it. But oh yeah, and there's links to these below. So if you're interested in just perusing, they have been scanned already. Like I haven't scanned them, but there are places on the internet that they already exist. As usual, like last time on the Museum of Everything Else YouTube channel, next week's video like this is already up on the Patreon. It's open for all patrons and stuff. So if you sign up to any tier, you can see it. It's already uploaded. It got uploaded when this went live. So if you want to see the next issue, well, it won't be this issue. It'll be another magazine. Then go and check it out over there. And yeah, if you enjoyed this, then don't forget to subscribe. Wait for next week's. And yeah, I've been Sam, and have a lovely time.